Hello, 9th of April. I just wanted to get started on the last problem of the section. And you can see how fast I can do it. This Fourier transform, I think, already is in the text. So I'll just pause and try to find it. It was there on page 85. Oh, I missed this. This is something new, I think. I don't think that was in the book. No, it's not. So this is where it comes in. So that means that what I wrote up here is the wrong function. I just missed that it wasn't x squared, or the norm of x squared. All right. So much for being able to read a formula. We must start with this. So back to A. Let's start with one function. So the scalar product is this is x1 omega 1 plus x2 omega 2 plus u1 omega 1 plus u2 omega 2. And then we must take the norm and square it, or norm the absolute value and square it. And since it's real, it's the same as just squaring it. So I believe this omega should be square root 3. That was the challenge. We should of course start with just x times omega squared, so that be h. The only idea I get is to diagonalize the matrix. but then it's not symmetric in the 2. I need to think a little about how to go about this. I've thought a little about it, and I have 2 ideas. One being to expand this and then complete one of the squares, and the other to diagonalize the matrix. But I think it's the same work, so let's apply the simplest method. So, and let's take it with W being 1.omega, and omega is minus 1/2 plus square root 3/2. So it's x1 squared plus 2 omega, x1, x2 plus omega squared, x2 squared. And then we take this part first. Oh, then we will get an x2 squared. And all right, let's see what we get. Omega x2 squared. That was silly. We have x2, so I can't do without that. The conclusion is we need to diagonalize the matrix. Okay. X dot omega squared. So we write it like the row vector times the matrix times x, and we have to diagonalize this matrix. I don't want to do that by hand, so let's Maple do that. I wonder what's up. I opened Maple, entered the matrix, metric matrix, and found the right it's eigenvectors, the right command, and did it. And one of the eigenvalues is 0. And my first reaction is, now that's impossible because omega is not a rational number. So how can an integer combination of a and b give 0? But of course, when we take the Fourier transform, we are working with real coordinates, not integral coordinates. So minus omega 0.1 is the eigenvector with eigenvalue 0, and 1 omega, the one with eigenvalue omega squared plus 1. And what? Oh, it needs to be equal. Never mind. That gives minus omega. It couldn't possibly. It is positive definite, so the 2 eigenvectors must be positive. I have the wrong equation here. So I'm confusing omega with the third root of unity on the unit sphere, complex unit sphere, the same as I'm suspecting Professor Koblitz of doing. If this is omega, oh, why was the square root? And then I wonder, omega squared expand. So it's 3/2. Is that important? I don't know. Well, back to the computation here. So we define new variables. Y equals you know what? I can feel I'm not ready for doing these things. It's very basic, and I don't know exactly how to define the new variables. So I'll finish for today, and maybe I'll do it a little on paper and then show you the result. We'll see. Otherwise, it's time for coffee. It's Monday, April the 10th, and I'm just home from Easter lunch at my family's. And I wanted to work a little more on this problem. When I awoke this morning, I thought about this, where the eigenvalue of this, one of them are 0, which is utterly impossible because it should give the norm of x, which only gives null when x vanishes itself. So I think we should accept that there is a typing error, and I think it should be the norm of x plus u squared. But I decided to reverse engineer the problem first. And we have the sum here. This is the character chi, and we need to single out those values of x that give the same value of chi, and therefore we must use that chi is a character modulo 3, which means that we will write x (3m plus a) and y 3n plus b, where a goes from 1 to 2, 0 to 2, and b as well, and m and n being integers. And then we take a factor 3 out here and sum over a and b, take the summation of n, m and n out. So it's the summation of a and b, And then we can take 3 out here. And this becomes 3 to 2s. You see here I'm running into a problem, because when we do this, I would like W to be 1 point, and then not omega, but a real guy, namely 1 plus square root 3 halves. So that the norm, when summing over the lattice spanned by these, my idea is to sum over a lattice where the scalar product gives the norm of this, but then we won't get this because we will not multiply by omega, but by the or maybe we can let omega be complex, or be complex. I'll just write it down. The scalar product, won't it be plus, and it should be minus? Oh, that's because I've got plus 1/2. That's not what it should be minus if we wanted it to be the norm in z extended by omega. So let's do this one over this lattice, so that these guys agree. What I'll make agree is then chi of a plus b omega and the norm of this guy. Then I don't think this is a problem at all, really. All right. So W is 1 comma omega, where omega is the complex number, but this is the lattice we sum over. No, it can't be. But if we are using integers, then I can't get the right norm. All right, that's where I stand at this moment. So I think my idea of reverse engineering the problem is the right one, but I don't know how to get on from here. They are summing over the integers. And then we have some very interesting complex guys occurring here. I don't like this. I will take a break and work on it later in the evening, And if I find out how to reverse engineer it and come to something that I believe will work, then I'll make, or when I do, I'll continue. Tuesday, April the 11th. It turns out that yesterday I actually had my theta function here. So instead of summing over this lattice, let's take out the theta function and then write it as I think it should be. So here x, we must sum over x being equal to m point n, and mu is a third plus b third. And then time dot 1 point omega, and then e to minus pi t. And then we should have the norm of this guy as well. And that's what I misread here. I didn't know what these vertical lines meant. So it's the norm of the same guy. And if we just consider theta of t, theta naught of t, then it x dot 1 minus x e to minus pi t x1 squared minus x1 x2 plus x2 squared. And therefore we can start with taking the Fourier transform of this, and then afterwards we differentiate in such a way that we get this. That means the first step is the Fourier transform of this guy, and the next step is to choose an appropriate differential equation, a differentiation. And one way is to diagonalize this quadratic form. But let's use a simpler technique. That gives 1/4, so there are 3 quarters x2 squared left. And this calls for a change of variables. Let's call them u and v. Let's do it as a matrix. So Z equals (1 minus 1/2) naught square root 3/2. There's Z1 point Z2. And we need the inverse as well.
determinant is 2 square root 3 halves. So now I've learned to find the inverse, learned again how to find the inverse of 2 by 2 matrix. I'll just check it. Square root 3 halves, square root 3 halves, naught and naught, right. And that means the Fourier transform. And this is x dot y, the normal dot product. And x we write as this, m to minus first z dot y actually we are integrating over x, so when we integrate over z instead, we need to multiply by 2 divided by square root 3. There we go. And then to be able to use the Fourier transform, we put this matrix on y. So that's the m star that pops up again. M star of y. And this is the dot product with itself. Yeah, we'll do it one step at a time. Square root t halves, 1 half, naught 1. I'll just multiply it in, I think. Unity, naught. 1 divided by square root 3. 2 divided by square root 3. So it gives y1 0.1 divided by square root 3, y1 plus 2i, y2, I mean. And we need the norm of that squared. Y1 squared plus twice the product plus y2, the second part squared, and this was y1. So that's can this really be right? 3 plus 4, that's 7. Let's take 1/3 outside. 7y1 squared. It should have been 4, shouldn't it? Plus, oh yeah. I believed that it should give 1/3 the norm of y1 minus omega y2, or minus y1 plus omega y2, so I think I have a mistake here. I'll just go through it again before I carry on. I did discover another mistake. There should be x2, but it's very simple. 3 plus 1 gives like 4. Which was what I expected. So it's 4/3 times the norm of this guy. Right. That was the first step. Next, I can write that here. I'm sure that will come in handy. Next, we must consider a differentiation of f w dot the differentiation of f which is of course w1 times 2x1 minus x2 plus, I'm using this guy, and then differentiating with respect to x2 that's minus x1 plus 2x2, nice symmetric, but it should be equal to minus 1 plus, x1 plus x2 omega, meaning x1 plus minus 1/2 plus square root minus 3/2 x, I didn't know I could do that, times x2. We need to solve this for omega 1 and omega 2. First, the guys involving x1, that's 2 omega 1 minus omega 2. Let's just do it here. Equals unity. And then the one with x2, that's minus omega 1 plus 2 omega 2 equals, well, that's omega. That's two equations. The discriminant is 3. And d1 and then we can use the Fourier transform. So d of x equals yeah, x times omega that's nice. This guy and this guy has the same norm. No, it's plus. That changes stuff. Let's look into that later. Well, we define, oh yeah, we even have to make a translation now before we can define our theta function. I'll copy what we need to the next page, and then we can define our theta functions and prove that they have fast decrease to infinity and naught, and then we can embark on the Mellin transform. I discovered two mistakes on this page. First, when we differentiate, we do get minus pi t here. I'll just write it. And I forgot this number 4. Yeah. And that means that if we take g to be this, then we must divide by pi t. So we are left with, and the minus we must add, so we are left with this. And then the translation formula gives this. Therefore we can define theta mu of t as and then by Poisson's addition formula, it's equal to this. Let's write y instead. Don't know why. And then we get, as usual, that that when mu is distinct from naught, or not distinct from any integer, this has fast decrease for t going to naught as well as infinity. Therefore, we can finally define the Mellin transform as it is. Now that was silly. We need to sum. Yeah, they first define this. Yeah, so we take the Mellin transform of this guy, of course. And then when we use h, we must insert the correct mu. So h actually depends upon mu. No, oh my God. I should just call this theta of t. There's no need to write this. So we have the sum. And for a real part of S being larger than unity, we should be able to exchange sum and integration. And since h has this term, here we have a g, which doesn't depend upon t, we can put it outside the summation. Or outside the integration. And you know what? I need to write it on paper. I can't collect all those thoughts while writing on the tablet. Oh, that took it something like 20 minutes. I went through the whole calculation again and ended up with this. The integration gives a pi to minus s, the norm to minus s, gamma s. And then we just make an abbreviation for this. We can call it T for term, T, and then divided by, or should we say the norm of T to minus S. And going back to the first, we can see that what we have is exactly this, and that's 2 times 3 to 2 s of ls. This is a little weird, I think. This, of course, is an entire function. Oh, that just means that L has zeros, where this guy has poles. All right. So we isolate never mind. So it becomes, because 1 divided by gamma s is an entire function, we have that this guy is an entire function of s. Well, that was part C. And it's time for lunch. Back after lunch. Let's try to get a little further. I copied this definition of lambda and the transformation formula up here. So let's apply that instead of going back to this expression. That means that this guy is equal to all of this. there's a constant we can put out in front. And then the norm. Was that y2? Yeah, this was exchanged, and this changed sign. Oh, that's a little weird. I'll just check that. I don't know. Ah, it comes from here. We'll just take it from y. So this is where the problem comes. So it seems right. That means it's m plus n omega. And that parenthesis stops here. All right. And then t to s, dt per t. And I've didn't apply this t squared, so we'll just have to subtract 2 up there. T to s minus 2. So that's actually one detail we've got right, that we get some function of 2 minus s. This is the only place where we sum over a and b. So that's what they called for given n at point n. Mm-hmm. So we need to compute this guy. And since we are with a specific curve, it can be done explicitly. And I already did that. I typed in the rows are a, so here in the first row a is 0, a is 1, a is minus 1 or 2, and the same for the rest. That's the coefficient to omega, and I just write w instead of omega. And this 0.1 is omega. It must be multiplied by omega squared to give unity. And 1 plus 2 times omega lies in the ideal, the first prime ideal, as does 2 plus omega. And of course 2 must be multiplied by minus 1 to give minus 2, which is equivalent to 1 modulo 3. And then we just compute the sum. I won't call it a Gauss sum, but maybe it is, and I just don't understand it. So we just use the definition, and when a is 0, we must use entry 1, so we add 1 here. And then we simplify with the equation omega fulfills. And then the first time I wrote it, I realized that those not giving 0 were a multiplum of 3, so I just divided by 3. And then this is what I get, and it's much safer than I could do it by hand. It may be wrong, of course. And that means that I need to make a table of these results. There seems to be a connection here. It seems very much like a transposition, but of chi itself. But if we transpose it, then we see that these two rows must be interchanged, and that is equivalent to changing sign. So this means that this is equal to theta of, this was b plus a omega, and then it's b minus a omega. And that's amazing, because that's exactly, oh, is it? Yeah, that's exact, no, that's not exactly what we have here. B plus, oh, but then the minus here, we can exchange sign. Can we do that? Let's see. I think it was quite obvious we could change sign here. That I had freedom of, that was the norm, whether I would use minus y1 plus omega y2. Oh, let's write the result, then I think it will come out easy to check out easily. This minus seems all wrong, though. Also, this imaginary unit changing phase across the symmetry axis. S equals 1. Well, we'll see what happens. So we are back to summing over m and n and integrating. Chi of b plus a omega. No, that's wrong. It should be m and n. Yeah, I need to get this right before I go on. And I also forgot the factor 3, by the way. So it should be 12 up here. That could eat 1 square root 3, never mind. Yes, we are left with the problem, but we are in a better position before, because now we know that this is right, because minus n plus omega n has the same norm. And that means that this is where the error lies. A week have passed since the last recording. I've had very little time to do what I said I would do, try to sum over the lattice instead of over the integers. And basically I thought the two methods would be equivalent. Maybe I made an error summing over the integers, but it seems I can come through summing over the lattice. Let's try to do that. That means that our G is defined just as the elliptic curve of this book, and we sum over the lattice, the real lattice giving the right norm, which is given by the dot product over r squared, and then we define lambda as the sum of all the thetas, or the Mellon transforms of the thetas, that was the base. Let's just see what that gives. We don't really need to know what W is, but I can just as well write it. And then this must be made to be omega, meaning that the second coefficient of W must be I thought I needed to do algebra with this coordinate, and that turned out to be very difficult, but we'll come to that. And then for each chi, we get the sum over n plus a third times omega, plus m plus b third third times omega. Oops, and this is of course the Mullen transform we are applying here. Pi to minus s gamma s and norm of, and that's the same number, to minus s. Here we take a factor 3 out, and in here we have the scalar product with itself, so we must take a factor 9 out to get the norm of a plus b omega. Meaning we get pi to minus s gamma of s, and then 3 to minus first, and here we get a factor 2s, and then what comes out, I believe you can see it, is just the L function of e point s. Well, when we take the Fourier transform, we must sum over the dual lattice. And I spent at least 1 hour working on the dual lattice analytically. But in the end, it became clear to me that we can actually do it geometrically. That was when I was lying in bed 2 days ago in the morning, waking up slowly, I got this idea. So let's have a lattice with a right-hand generator set, and then V1 must be orthogonal to V2, and the product of these two must be, the scalar product must be unity. So now if we call the angle between the two guys, let's make that black, for theta, and then going pi halves, radian back, it becomes theta minus pi halves, the angle in here. Meaning that u1 times v1 times cosine pi minus theta minus pi halves, which of course is equal to sine of theta. Let's just do that. Must be unity. And V2 must be orthogonal to U1. So it must go up here. So that the angle between these are pi halves minus theta. So equivalently we get u2 times v2 times sine theta, this unity. So we have the length of vi we work here in r squared, but by multiplying with w, it's isomorphic. I don't know how we should say it. A diffeomorphism, I don't know, and additive group isomorphism with the complex numbers. And what we will be doing later is to multiply v1 point v2 with minus I. And that means that we rotate them 90 degrees backwards, or minus 90 degrees. So you can see V1, which was orthogonal to U2, is rotated to minus U2. Oopsie, yeah, it's minus U2 in the direction of minus U2. And it has this length. Times minus U2 and minus I V2. We have V2 up here. That's proportional to U1 and it's in the same direction. So it's a positive factor. So it's plus 1 times U1. And that means that without doing the complicated algebra, finding the dual lattice or dual basis, and then computing this and reducing it, we can actually write up the result from geometric considerations, which is very nice. I forget the formula for using the dual lattice, so I'll just find that. That's problem 5b. So the sum over the lattice is the norm of the dual lattice is the norm of the determinant of the lattice times the original one. So it was 1 divided by the determinant, and it's square root 3/2 times the sum over the dual lattice, and then the Fourier transform of x. Oh, shouldn't we write y here just to... yeah, let's do that. And we make the substitution with the reciprocal of t, so that the integral itself becomes minus I pi to 2 minus s gamma of s minus 2, and then the norm of y to now what's that? That's 4 minus 2s. Oh, the norm. Now what did I write here? I wrote, oh yeah, x dot itself. Yeah. So it's 4 minus 2s. It's, yeah, so that becomes the norm to 2 minus s. Of whatever y is. Oh, it should be, that's a mistake I made. Here it should be x plus x plus mu squared. There we go. Therefore, this becomes this. You can't see it. This is the same as this, x plus mu. And here we sum over the reciprocal lattice, and then we need to have the norm of a point in the reciprocal lattice. There was a formula there which I forget, something like 3/4, 4/3 of the not of the original point, but of yeah, I need just to take a little look here. After 1 cup of coffee, I'm ready to carry on. First, we missed the equivalent, and second, I missed 2/3 here. You have to live with not being able to see me. Do you think you can handle that? That was 2 divided by square root 3, and then equivalent sign. And then minus, let's take it one bit of the time. First, there is a summation here, which we need to deal with. And we have an imaginary unit missing, so it becomes, the third root here gives omega to a times and y, that runs through the lattice, so that's v1 plus b times v2. That will not give integers in general. It will give a real number, of course. Oh, I need to look at that. And second, this minus v minus I times v, that's 1 divided by sine. That's another one of these. So what we are missing is computing this sum, working on this sum. So it's times and then of course getting from this to actually summing over. Oh, it's u, and divided by sine. Oh my god, that's too much I'm doing without keeping proper track of it. So this is u1, no, minus m u2 n u1. So we are back in the original lattice like we are here. And where were u2 here? Oh, there is a factor here as well. Yeah, I'm trying to do too much at once and I can't recall the individual formulas. So, another break, and then I'll find all we need. Another cup of coffee, and I realized that part of my confusion was that there was no mu in the Fourier transform of G. So we get this and no more. And then we just miss this sum. And the problem here is that they must actually be summed over the lattice, or rather the dual lattice. And that means that we must we must actually find the dual lattice and then put omega in those powers, and that's like something square root 3 halves, and I'm quite sure that will give nothing we like. And that means that this method neither works for me, but I've transformed the problem into computing this sum. I will make a numeric test of it, but as of now, my conclusion is that I'm not able to derive the reflection formula. I tried summing over the Gaussian integers and then having a special norm, and that led to summing over the where is it? The wrong numbers here. And now I get the right numbers, which is nice, but then this sum, I'm sure it will be dysfunctional. Hello, gentlemen. It's now Saturday, April the 15th. This morning I woke up and realized I've made a silly idea, which should be on this page. That's w.y, which I just wrote out to be this, and that's not exactly what it will give. We have 2 plus omega third y1 y2, and this is minus 1/2, so that's 3/2 plus square root 3i divided by 6 y1, and this is minus 1 plus square root 3i y2, and now let's take square root 3i outside parenthesis. And what have we got here? Now where did the 3 go? We just leave that, write it down here, divided by 3. And that means this gives 1/2. And this 3 divided by square root 3 isn't that square root 3i? Terrible writing. Halves times y1. Now that gives 6, and that gives minus 3. So it's a minus. And that means that it's I divided by square root 3 times y2 minus y1 omega. And that was exactly what we needed. And because I didn't get that, I had an immense amount of confusion. I still believe it should be possible to do it by summing over the dual lattice like I tried, but I guess from here on it's just a question of doing it a couple of times. And this afternoon I did it once. And then the Fourier transform. There we go. If you could read it, you'll see that I'm a factor 2 and a factor 3 off. Or was it? Yeah. So I guess at some point I should have multiplied or divided with square root 3 halves and did the opposite. I believe the next time I go through the calculation I will get the right result. I almost did this time. I must just show you that I actually, to verify my idea this morning, made these integrations. Maple can do them just to verify that I did get the right result. Here we have a plus b omega, and then this is the Fourier transform. So this should be exactly this times something. The factor was 3/4, and that might be where I made the mistake. Who knows? Well, that finishes my work on section 5. That was most interesting, but my God, it did take a long time.